I just went to a math conference called the Gathering for Gardner in Atlanta. It happens every 2 years. I met a lot of great folks there. I got to meet Jaap Scherphuis, who is also makes YouTube videos about adding machines. Within 10 minutes of meeting him, he whipped out a Kurda. It was amazing. I got to play around with it and got to hang out with him along with some other folks. One great thing about this conference, the Gathering for Gardner, is that there's a gift exchange. Everybody who comes, anyone who wants to participate, brings a little gift. You got to bring like 200 of them because everybody else is going to get one of yours and you get one of everybody else's. And so I thought, there's lots of things in the gift exchange, and I'm going to show you a few highlights of some interesting mathematical objects that I got in the gift exchange. Hopefully it's interesting. If not, it's alright. Alright, first I got some little handmade things. This one is a little 3D printed Klein bottle on a keychain. I like this. The Klein bottle is a very well-known topological shape, and I'm into topology, so I like the Klein bottle a lot, and it's just a nice little doodad. It says this was made by Daniel Matias, so thank you very much, Daniel. Here's another little thing. This is a Sierpinski tetrahedron. This is a fractal shape, and it looks also 3D printed. It looks kind of fragile, but yeah, pretty great. This is made by Hideki Tsuki at Kyoto University. I hope that I pronounce the name correctly. Please forgive me if I mispronounce any of these names on here. And he says that you can make cool shadows with it. I'm going to try. He's got some YouTube videos of this thing in action. Check them out. I'm going to try and put links to all of the creators in the YouTube description down there. This is a pair of puzzles on paper. The gift bag contains many puzzles on paper. Which I'm just giving you the highlights here. But these are two puzzles by Eliza Gallagher and Neil Kalkin, and they're kind of Sudoku type puzzles. But what's interesting to me about these is these two puzzles are kind of linked. You fill in the numbers, right, like a Sudoku. It has some special rules. But then this red column on this one is actually the same as this red column. So after you fill some stuff in, maybe you get some of these numbers, you're supposed to copy them into these numbers, and they will help you get some stuff over here. And then if you get more red numbers, you copy them over here, and that'll help you finish this puzzle. And the yellow one and the yellow one are linked in the same way. So it's kind of a Oracle of Ages, Oracle of Seasons kind of situation here. I haven't tried this one out yet, but I like the concept. And if you follow these links here, I'll copy them in the YouTube. You can see, you can download and print them out for yourself. Check it out. This is a hand-colored handkerchief, and I hope this one, unfortunately, is the only one that I'm not 100% sure the name of the creator. I was going through the box full of stuff with my daughter, and when she saw this, she immediately grabbed it and was like, "Oh yeah, I want that." And I think it had something with it to indicate who had made it, but she immediately got rid of that thing, so I no longer have the name. But looking back at my program from the conference, I believe that this thing was made by Lauren Siegel, and what it is, it's a handkerchief which has been dyed in a particular way. She folded it up in some way. It looks to me like this had a diagonal fold in it, and then she dipped it in some ink. Right? There was no. She didn't paint any of this on. It was just folded and dipped. And then you get this kind of interesting symmetry pattern on the resulting thing. Come on. You get interesting symmetries here, right? And this is something that's been of interest to mathematicians for quite some time. What types of symmetry patterns can exist in a two-dimensional figure? And this one has certain types of symmetries, like this image over here is copied over here because of the folding. There's also kind of a reflection type symmetry of this part, and there's some other reflections. Symmetrical patterns on flat surface can also have rotational type symmetries to them. And these have all been classified by mathematicians. These are called the wallpaper symmetry patterns sometimes. And it turns out there's only 17 possible wallpaper type symmetry patterns. Any sort of symmetrical plane figure has to abide by one of these 17 types. And this person who made these also gave a talk at the conference about which of these 17 symmetry patterns can actually be achieved by folding and dipping. I thought it was an interesting talk and a nice little thing here. Thank you for that. Here's the thing, which is very nicely produced. This came from somebody who operates an Etsy shop called Serious Enigmas. That's what this says. Serious Enigmas. This sort of weird looking font is weird looking because when you flip it over, it says the same thing, Serious Enigmas. This is called an ambigram. And anyway, this is called a Celt or a Rattleback. Maybe you've seen this before. Pretty great thing. I really love these Rattleback things. What it is, it's just a piece of plastic here. There's no magnets or moving parts or anything like that. It's flat on this side, and then the other side has this sort of a bend to it, a curve to it. But if you look carefully, I don't know if you can tell, but the shape of the curvature here is not exactly symmetric. It has a weird asymmetry to it, and that asymmetry causes the Rattleback to do its special thing. So, for example, you can spin it, and actually this is put on this sort of cute little Magic 8-Ball style decision-making spinner platform. You spin it, you see that? It goes the other way. Actually, this thing, because of the very particular weird shape about it, it likes to spin that way, but it does not like to spin the other way. You spin it the other way, and it changes it up, right? You ever heard of the conservation of angular momentum? Not this thing. Oh, I got one of these in the box. I don't know about that thing. Some guy, I don't know. Here are some dice from an outfit called the Dice Lab. I believe the person who runs the Dice Lab was there at the conference, and they gave us some sample dice. These are pretty great. They're sort of D&D style dice. Oh, this one looks like a standard D10, 10-sided, but it's actually, hey, I got a 10. This is actually 14-sided. Where's the 14? I don't know. There it is, the 14. 14-sided. Do you ever want a 14-sided die? I don't know, but here it is. D14. Thanks for that. And this one is a little more interesting to me. This is an 8-sided dice. 8-sided die in the standard octahedron shape. But actually, if you look closely, it's not the standard octahedron shape. Each face of this is a triangle, but they are not equilateral triangles. Typical D8 would be made up of equilateral triangles. But they're not. It turns out each face actually is the same shaped triangle. They're all congruent figures. And they make this kind of lopsided or sort of geometrically weird octahedron. And this is part of the collection they call Skew Dice. This is specifically tuned so that even though the geometry is skewed in this weird way, it is still true that every face of this die is equally likely to come up. So this is still a fair die. No, the geometry doesn't favor any particular one of these numbers. It's still a fair die, even though it has this skewed geometry to it. Pretty great. Thanks, Dice Lab. On the theme of dice, here's another one. This is actually much more mathematically interesting. These were provided by Ali Munoz. I think I said that right. These are what are referred to as non-transitive dice. So the two dice, and actually Ali provided detailed instructions about how you're supposed to do these properly. And I'm just going to explain to you one of the ways that you can use these just with one die. This is like you can challenge your friend. I'm going to roll the die a bunch of times, and the person who wins is the one who has more of their color come up. So you choose a color. Each person chooses a color. Say I'll be white. You be blue, right? And now blue wins on this one, or white wins on this one because there are no blues. You just see who has more of their own color comes up. The interesting thing about this is, so the colors here have been selected in a very particular way. And the way that it works, this is if you know the trick, you can beat your friend. The colors have been selected so that, in particular, the white will beat the red more often. So statistically, if you're going to roll it a bunch of times, it's more likely that the white will win above the red. It is also more likely that the red will win above the blue. All right, so the white will beat the red will beat the blue, but here's the crazy thing: the blue will beat the white. All right, this is why it's called a non-transitive dice, because it has this weird sort of paradoxical kind of circular relationship. The whites will beat the reds will beat the blues, and the blues will beat the whites. What that means is, if you're going to play against your friend, you let them choose a color first, and then there's always a color that you can choose which is going to beat their choice. Very strange, very clever the way that this is constructed. We got 2 of them here, and there's a little bit of instructions here about some variations you can do. You can play weird tricks with both dice. Very cool. Thank you for those. I have 2 very nice wooden, like custom cut wooden constructions. This is a puzzle by George Hart, who he called this a warped grid puzzle. If you can see this is a picture of more or less what it will look like when it's done, although it's not straight grids. It's got these weird jaggedy shapes. But it looks like it sort of has a bulge in it, but it's actually totally flat. Very nice, very kind of intricately cut. And George Hart gave a talk at the conference about how he constructed these this weird kind of bulgy thing. Basically, he made a more or less ordinary looking sort of rectangular, mostly 90-degree angles type puzzle, and then he warped the whole thing on a computer, and then made these interesting looking pieces. If you stick around to the end, I'll show you. I'll do it in fast motion so you can see what it looks like. I like it. Here's another homemade laser cut wooden puzzle. It's called Build 14 Bridges. This was the 14th gathering for Gardner conference, and so many of the items that you got in a lot of the talks were based around the number 14. This was designed by Ryuhei Uehara. I hope I said that kind of right. Here, the idea is you get a bunch of these bridges, and they have different heights. There's kind of a tall, a medium, and a small one. These are the mediums. And you just got to fit them all onto the board, right? They go this way. But actually, if you just line them all up straight, there's 14 of them. There's no way you're going to fit them all on there. So you gotta do some kind of weird tricks with them. They will fit at other kind of angles, like they fit like that. So you have to fit all the pieces in. I'll show you at the end how to solve this one too. It's very pleasing, this one, once I figured out how to do it. Thank you, Mr. Uehara, for that one. This one here is very mathematically interesting to me, and I'm really glad to have this thing. This is called a golem ruler. This is based on a concept invented by Solomon Golem. And this one, I don't know if you can read the words here. It says this is designed by Ching Mao, John Bohannon, and Yuan Mei. So thank you to you 3, and sorry for not saying your names correctly. This is a ruler with standard markings. So this side is inch markings, and on the bottom we have centimeters. And you'll notice only 0, 1, 4, and 6 are marked on the top for the inches side. This is the whole trick with making a golem ruler is you want to make this ruler, which goes up to 6, you want to make it so that it can handle measurements of any whole number distance, but using the fewest number of markings. And this is kind of an optimal arrangement. This can handle measurements of any distance up to 6. So you can do distance 1 is between 0 and 1. You can make distance 2 by going 4 to 6. Distance 3 you can do by 1 to 4. Distance 4 is 0 to 4. Distance 5 is 1 to 6. And distance 6 is 0 to 6, right? So you can measure any whole number distance from 1 up to 6 using only 4 markings in this case. The one on the bottom goes up to 17, and actually I'll let you think about it, but you can measure any distance from 1 up to 17 using only these 6 markings. This is actually a very computationally difficult question to try to answer, which is if I want to measure up to some amount, say up to 25 or something, exactly how many markings should I use and which ones should I use? It turns out there is no good formula that answers that question. So it's an example of an NP-complete computation to construct golem rulers of some arbitrary length. So very cool. Thank you for this. I'm into it. And I got one more. This is a very ambitious 3D printed object by George Bell. He calls it the flippy top. This is inspired by what is more familiar. It's called the flip top, which is a little spinning top. You spin it, and it's got sort of a hemispherical bottom to it with just a post sticking out. And the idea is you spin it. I don't have one, or else I would show you. You spin it by spinning the little post on top, and its spinning motion is unstable in a way which makes it want to flip over. And so this flipping over is not very easy to understand physically, and to be honest, I don't really understand why exactly why it works. But it has to do with the fact that the bottom of the top is heavier than the post sticking out on the sticking out vertically, and this extra weight on the bottom causes the spinning to be unstable. But once it flips over, that is a more stable arrangement for the top, and so it likes to stay flipped over. Anyway, this is something like that, but it's just got two hemispheres, so this is just a sphere, I suppose, although it has a hole drilled through the center of it, and inside the hole there, I don't know if you can see it, you can hear it, inside the hole is sort of a heavy metal ball, and you spin this thing, and the idea is if I spin it right now, the ball is on the bottom, and so the bottom is heavier. And so right now, if I spin it this way, it will act like a flip top, and it will want to flip over. So I spin it, and it flips over. But once it flips over, the ball drops down to the other side. And so now that causes the instability again, and it will want to flip over again. And so if you spin this super fast, what you will see is it will just continually flip over up and down several times. Now, unfortunately, because it's like a complete sphere, it's quite hard to spin this without it just like flying away like that, right? It works best if you can put it in like a shallow dish or something so that it's not going to fly around. And I have had a hard time making this work well. Check out George Bell has some videos of this on YouTube, which I will link, that where you can really see it spinning and flipping. You can tell it flips just because you will see the color go back and forth, and you can also hear the ball. Yeah, you like that? Great concept, very very interesting. Thanks, George. All right, that's all I got for the highlights. Thank you so much for everyone who contributed to the gift exchange. Let's do that puzzle. There's no picture on here, so it's, you just have to match up the shapes. And the only clues you get is, one thing is you can see that there is a direction to the wood grain. Here it's going vertically. And you can also see the bottom right corner has George Hart's little signature on it. And also, you can kind of tell the difference between the colors. It looks like one side of the wood was stained in a slightly different way or something. So you can flip them all up the right side up. But other than that, you got to just match up the shapes as best as you can. We'll see how I do. Yeah, how do you like that? It's got like a bulgy bulge in it. Alright, here's the bridge one. Unfortunately, I broke one of the little feet off of these things. Sorry. Alright, so there's one little trick that it took me a little while to figure this out, but it's the internet, so I can tell you. So this thing can go like that, but you gotta kind of nestle them together as well as you can, but you can't fit very many, even if you do that. These are all the short ones, which have to go in first, I guess. But even now, how am I going to get this guy in there? I only got 4 of them in there. There are 6 total short ones. Check it out. You can nestle them like that. I suppose is a little bit better. But then here's the real deal. This one can still go here. I'm going to sneak this guy under there, just like that. Huh? How you like that? That's the pro way to do this. All right. And now this one, maybe I'll use the broken one here. It's going to go there and right there. You sneak it under. I suppose it's a little easier when it's broken, but you could have done that even if it wasn't broken, right? And then this one I'll put here. So I fit all 6 of the short ones in, and now I can fit all 6 of the medium ones in the same arrangement up here. Maybe I'll start with this one because this has to get nestled under that. There we go. And I will fit these guys in here. Two more of these guys. What happened? Oh, another one hit on this side. All right. And then I got two tall ones. What? Oh, I've done it wrong. Like that. Yeah. All of these need to be twined. One goes here. All right, and then one goes in there. You got to sneak them in. Right there. All right, now I'm feeling good. Yes, and now these two go just across the top. How you like that? Isn't that a nicely pleasing little puzzle there? Thanks a lot for the puzzles.